Today we're going to look at how to multiply vectors. There's two different ways vectors could be multiplied together. We can take a dot product, which is sometimes called a scalar product, and we can take a cross product, which is sometimes called a vector product. If you take a dot product, the result will be a scalar. You'll notice there's no vector symbol above the letter here. If we take a cross product, we get a vector out of it, which you can see by the notation here. We're going to use matrix math to figure out our dot and cross products. There are simpler ways to do it for some situations. However, following these methods will work for any vector that's in engineer's notation. I have a force and a displacement listed in engineer's notation. The first thing I need to do is label them as 3x1 matrices. To take a dot product, I multiply the same components from each vector. I then add the other components multiplied together. So this is what it will look like. So I have the x component, or the I component of the force, multiplied by the I component of the displacement. Now I'm going to add the product of the j components. So I have the product of the j components. Now I'm going to add the product of the k components. So I have all of my products set up. I need to do the multiplications, trailing the units along, and then lastly I will add each of the pieces together. I finish the multiplication. I have 3 newtons times -2 meters is -6 joules. -2 newtons times -3 meters is 6 joules. And 6 newtons times 2 meters is 12 joules. Now I just need to add all of these together to get my total work. A total of 12 joules of work was done by this force through this displacement. Again, multiply each of the components together and then total them up at the end. Now let's take a look at a cross product. In this example, we have torque is equal to a force times the radius that it's acting over. We're going to do what we call a matrix determinant. In order to find the determinant of a matrix, we need to start with a 3x3 matrix. The first row of my matrix will be my unit vectors, I hat, j hat, and k hat. The second row in my matrix will be the one listed first in the equation. So I need to plug in the values that match up with each of these unit vectors. And the bottom row of my matrix will be the one that is listed second in my equation. I fill in the values for position in the matrix. As I solve this, I'm going to go ahead and write what my answer will look like. It'll make more sense here in a second. Since my answer will be a vector, I have the I component, the j component, and the k component. I've left myself lots of room because I'm going to need that room as I solve the determinant. The first dimension that we are going to solve is the I dimension. The way I get a determinant of a matrix, anything that is involved in that one, so the I row, the I column and the I row get ignored. So anything in the same column as I or the same row as I gets ignored when it comes to solving a determinant. The next thing I do is I multiply the two values that are diagonal from each other. So I have -2 times -2, which would be 4. I then subtract the other values multiplied together. 6 times 3, which would be 18. So again, in the I component, I cover up everything in the column and the row with I. I multiply these values together and subtract the multiplication of the next two values. We're going to use the same steps to solve for J. I cover everything in the column with J and the row with J. I do my crisscross again. In this case, I have 13 times -2, which would be -26. And I subtract the opposite corners multiplied. 6 times 4 would be 24. And lastly, I get to the K component. I cover everything that's in the column or the row with K. I start here. I have 13 times 3, which is 39. And then I subtract the other one, -2 times 4, which would be -8. So subtracting -8 would be the same as adding 8. Now to clean this up, I just do the adding or subtracting that's left, and this will bring it down to a single value for each dimension. Now that I've simplified, I've added in my unit, a Newton times a meter. In theory, would be a joule. However, when it comes to torque, we leave it as Newton meters. My torque would be -14 Newton meters in the I dimension, -50 Newton meters in the J dimension, and 47 Newton meters in the K dimension. And what you would find if you graphed these, this torque would be at a right angle to both the force and the displacement. We can use the right-hand rule to help us determine direction. That's something we'll get more into when we start dealing with torque